Hello everyone, welcome back. Hope you had a nice break. The next talk I'm very excited about because it's from Nexus, and I came across Nexus about a year ago when I found out that they'd developed a method to prove out using ZKP any general Rust program, which I thought was just brilliant. This is something that we really need, the ability to prove general computations like that in Rust. Marvelous. So I had a chat with them, and they do all sorts of interesting things. And it also turned out that their chief scientific officer is Professor Jens Groth. And apologies to all the Danish people for my pronunciation, especially Professor Groth. But he was at UCL many years ago when I was just starting out doing ZKP. And I remember I went to visit him to have a chat about it, and he helped me. He showed me where I got my maths wrong, which was jolly useful. So it's nice to see that connection there. But I think these guys haven't stopped with Rust. They're now talking about verifiable AI and verifiable computation generally, and this is, I think, a really interesting subject. So I'm very pleased to welcome Diego, who is going to talk to us about it. Hello, Diego.
Hello, how's it going?
Good.
All right, I'll get started. So, can you see my slide?
We can, yes.
Okay, perfect. So I'm going to talk to you all about the verifiable AI, why you should care about it, and why verifiable computation is so important in the age of AI. So, first, a little bit of introduction. Who are we? As you were just hearing about, we are Nexus. We are building a supercomputer by leveraging the latest advancements in cryptography. We have a team of researchers and cryptographers based everywhere from Europe and San Francisco, and I'm the VP of Engineering. So, what is verifiable compute? Just start from the very, very beginning. And not quite explain like on 5, but very basic version is that a prover can produce a small computer-generated proof that a computation was done correctly, and a verifier, another person, can check the proof without redoing the computation. And this proof has 2 properties, very simple, that they're hard to forge. If the proof is valid, you can trust the computation was done, and they're really, really easy to verify, ideally. There are 2 types of verifiable compute, as you probably all know, ZK, zero knowledge, and non-ZK. And the difference is, in the ZK version, the input and the output, the input, the witness is private. In the non-ZK version, everything is public. There's a surprising result here I want to highlight, which is that sometimes people think that the privacy or the ZK side comes with an extra overhead. It really doesn't. Most of the overhead, most of the technology is in creating the proof. So whether something is ZK or not ZK, actually it's just almost equivalent to a toggle or an option on the prover side. This is a slightly surprising result, at least it is to me, that the magical part, which is the zero knowledge, essentially comes for free just from having the proven technology. All right, given that just basic table stakes, I'm going to talk about some of the pain points in the age of AI and how verifiable AI can help address them. So what I'm going to do over the next few slides, I'm going to present a series of points, pain points, data points, that just kind of like helps illustrate, starts to paint a picture of how verifiable AI can help things. But first, let's address by some like actual use cases. And it'll be slightly, my intent is to just put a bunch of points out there, and then I'm going to connect them all at the end. So the first case I want to talk about is copyright-free LM generation. So how do you prove if an AI model was done trained with public domain data. The most classic version to do this now, of course, is to just open source the weights, open source the data. That takes some effort to even verify all the data is actually correct, verify that all the data is public domain. How do you prove it to another agent? And how do you verify if you have some data from an LLM? How do you verify that that data that was just generated came from a model that was properly created? So the solution to this, using verifiable AI, is you could actually create a succinct computer-generated proof, like we were just talking about, that the model was trained only in permissible data. So, for example, maybe public domain or specifically licensed data sets, so that you could have proof that this training was done correctly. You could have proof that no copyright material was used. The application could be publishing, and then you could have models that fulfill with like IP laws or sort of regulations of certain countries. Another use case or pain point would be, how do you prove to a government agency or regulatory body that an AI model, for example, say insurance or some other type, maybe hiring or lending, does not discriminate? And inversely, how do you verify that the model that you're using meets compliance or fairness standards without having to, even if you had access to the model itself, even if you had access to the weights, even if you had access to the training, it is quite difficult to easily, trivially verify this. So again, with zero knowledge proofs or even just non-ZK proofs, you could actually create a proof that says the decision from an AI model, for example, Alice was approved for a loan on April 1st, 2026, meets legal criteria. You can even have a proof that says Alex was approved for a loan based on the legal criteria of that time. And if the laws change, that's okay. If you have the proof, they have an auditable proof. This proof could show that the decision of the AI model, whether it be an LLM, whether it be more machine learning, was done meeting all the compliance standards without actually revealing the user data, or without even necessarily revealing the model. Maybe the company does not want to reveal exactly the inner workings of the model, but they just want to have a proof that they can show to the consumer the decision, and potentially to regulatory bodies that, hey, everything was done above board. Particularly tricky one, which I think is quite interesting, is accountability after data deletion. So if you have a GDPR compliant service, let's say an exchange or some other sort of web service, maybe they need to report specific criteria to a government agency at a certain time frame. But on the other hand, if it's GDPR compliant, the user has certain rights to have their data be deleted. So one of the challenges is, if you completely delete all the user data, you might not be quite in compliance. So let me give you an example. Let's say a user joins in January, and in May they ask that all the data be deleted. And maybe the agency had to be given like updates, January, February, March. So once the user asks to have their data deleted, in a traditional Web 2 world, you have a tension between the ability to the company to audit and to show that they were compliant every month up to deletion, and you have a tension with actually deleting the data. So here you could actually have a proof. The service can produce a proof that every month. In January, there was all the data was properly sent, and properly met criteria. So even if the user asked to have all the data deleted, you still have a record of the proofs, and the proofs can convince the regulatory body or even the agency that at every one point the company was compliant, and B, once the data was deleted, it was deleted, and none of it needs to expose any user data, and none of it needs to sacrifice any kind of compliance or any criteria standards. It's a pretty good way to use cryptography in a clever way to match security and privacy with like regulatory compliance. Another use case is model integrity. So let's say you have a hosted AI model service. Maybe, for example, the most obvious one is ChatGPT, where you have OpenAI that hosts the ChatGPT model, but you could also think about it as Hugging Face, where the model is not necessarily an LLM. The problem is, how does these services prove to their users that they're using the model they think they're using? How does a user verify that they're using that the model was not switched on them? It's quite easy for a web app to just switch the model that the user thinks that they're using. It's actually not trivial for your trust to be built here. So again, we can use proof. We could have a proof to the user that they are using the model they expect to be using. This might be important because they might be relying on a model that's more powerful. They might be relying on a model, going back to the earlier point, that's legally compliant, and they don't want something that's not legally compliant. Maybe they want the model where there was no fine tuning that they themselves did not authorize or were not even aware of. Maybe because of cost. There are some models that cost 5-10 times more compute than other models, but for the user, the quality of the model is not immediately obvious, but they want to make sure they're getting what their money's worth. So having a proof that they're getting the model they think they're getting is an easy way to build trust and verify. So as you see here, this is the last of these. I set up a lot of case points where, whether it be the users in a regulatory environment, whether it be the users using APIs for talking to models, whether it be using LLMs, whether it's about deletion, there is a growing body of needs in the age of AI for having computing that can be verifiable. Most of these problems today in the real world without verifiable AI are done through, as you would expect, non-cryptography. It's done through branding, it's done through legal, it's done through auditing, it's done through reading source code. Our proposal is that we use math proofs to make this stuff programmatic, simple, and easy. So let's talk about verifiable computing and a little bit deeper. Now that we've set up all these different data points, what are the patterns that emerge? So the patterns that emerge here is, one, verifiable model inference. Verifiable model inference is to prove that the AI model, just the inference, when you're talking to it, what are the responses you get, was correctly computed, and it meets the specification. To guarantee that the output is genuine and that you're using the correct model. This does not mean that the model was trained correctly. It just means that you're using the model that you think you're using, and then there's a proof with every piece of response. Whether the response is a piece of text, maybe it's a piece of image. Maybe the model generated an image. An image could come with an equivalent proof next to it that says this image was generated using Creative Commons data, or Creative Commons images. There's also verifiable model training, which is to prove that the model was trained on specific data sets following a claim procedure. This is, of course, as I was referring to, regulatory compliance, sensitive domains. You want to have a proof where the model was trained with the data you think it was, or you want to have a proof that the model fulfills certain properties, such as maybe it's only trained on data from, like I said, that was Creative Commons. Maybe it's only trained on data from this place, from this purpose. Maybe you want to train data. You want to have a proof that the model they're using was trained exactly how you think it was. And there was no. Maybe you want a model to make sure that nobody had any unauthorized fine tuning, so it's as pristine as you think it is, and that it's genuine. So now we get to the part where we talk about the state of verifiable AI. So I've given you some data points on how and some use cases. I talk about the two big broad areas: verifiable inference and verifiable training. But what is the current state of the world in these things? So the first obvious question, it's a very simple question, is how close are we? Well, there are two big problems that need to be really, really addressed, really, really solved to get to truly verifiable AI. One, it's quite expensive And two, there are many, many different types of AI models, so it's quite tricky. So the question is it pointless? No. There's a path forward. So let's talk about the path forward, given these two big problems. The first one is computational overhead. So this is one of the big things I like to always bring up because it's not always immediately obvious to folks. This number is always changing, but let's just say verifiable computing is around 1 million times more expensive than regular compute. What does this mean? Using simple language, it means that it's a program, let's say a Rust program, takes around a second to run. It'll take you 11 days to get the proof of the program. If it takes 3 seconds to run, it'll take you about a month to get the proof of that program. So it is quite expensive to get. Now, there are techniques to parallelize it and slice it. So maybe it takes one computer a month, but maybe it takes 1,000 computers just a few hours. So there are ways to parallelize it, but you still have to pay for the computing. So it is quite expensive. However, and this is a really interesting thing, one of the reasons that I personally joined Nexus, the verifiable computer industry has been making an order of magnitude jump every year or so for the last few years. This is quite interesting because whenever you see a corner of computing where it's making 10x jumps year after year after year after year, this is a corner of compute worth paying attention to. So we like to refer as like kind of the ZK or verifiable compute has its own Moore's law that is its own Moore's law on steroids, where it's just growing faster, and as it gets faster and cheaper, more and more use cases open up. So to give a concrete example, us at Nexus, we have a ZK VM, a zero-knowledge virtual machine where people can write Rust programs and have proofs be outputted along with the result. In the last year, it's already increased and improved over 100x. This is a combination of not to toot our own horns, not just our own cleverness, it's because the industry has been moving at breakthrough speed. The CS literature is a fire hose of innovations. The open source world is just a fire hose of improvements. So the ZK world has been making 10x jump constant. You could make a strong argument that 10x is actually the lower bound of the kind of improvements it's been making year after year after year. So if 1 million x is somewhere between 6 to 7 orders of magnitude, and the industry has been making an order of magnitude or more every year, it's not hard to predict that, or at least our thesis is, that we will be able to reach somewhere near close to 1 million. We're nowhere near plateauing or getting to some asymptotic point there yet. So that is a thesis that as ZK verified compute gets cheaper, based on this industry, then we're not slowing down anytime soon. Now, the second problem I mentioned is model diversity. I mentioned AI, but I actually pulled this light verbal trick. There are many types of AI. There's deep neural networks, there's convolutional neural networks, there's recommenders, there's LLMs, and they all have very, very different architectures. So the question is, can you actually have proofs for all these very, very different things? And the answer is yes. The simplest way to do it is to just build a general computing machine. So not have verifiable proofs, very easy to for specific models, rather focus on building a general computing machine where if this virtual machine, if it can run any program, then it can just return the result of proofs. So our thesis is that it's much better to invest on not application or model dependent or specific proof schemes, but rather focus on having a general compute machine and then just make that faster and cheaper and easier to use. Now, it could be possible, and it's probably very likely, that there might be optimizations or potentially precompiles for certain models if you want to make them go faster. This is not unique. There are many times when virtual machines have precompiles for certain expensive operations, usually cryptography, but there's also non-cryptography ones. So having pre-composite optimizations for certain models makes sense, but ideally you want to be doing it in a general compute setting rather than have some kind of ASIC or application specific one. And again, like I said, the state of the industry is there's lots of work happening all over the place. It's coming from academia research, also coming from multiple R&D labs like Nexus. I just mentioned a few. Nethermind, Brevis, Ezekiel. They're all just a tiny bit of the people that are producing work constantly, and we're all learning from each other. So it's very important, I think, in an open science way to give credit to all the different companies and labs and researchers. I can't name them all, but I just mentioned a few that are in the space. And that's it. Thank you. So if you're interested in ZK or verifiable AI, we're always hiring.
Well, Diego, thank you very much. That was fascinating. I particularly liked your idea of there being a specific Moore's law for verifiable compute, and I would heartily agree with that because I think you've got the normal Moore's law anyway, which applies to all compute, but
Right.
then you have some very good mathematicians attacking the problem from the other end, don't you? And those two things together are what give you this extra speed up over a conventional Moore's law.
That's right, and it's yeah. So I wasn't even talking about the whole GPU versus CPU thing, which is it's its own different form of acceleration. But yes, the math protocol breakthrough velocity has just been wild, and it's something to keep an eye on. Again, whenever you see a corner computing make 10x jumps year after year after year, you want to keep your eye on it.
Yeah, absolutely. So there are a few questions, and we've got a little bit of time. So if you wouldn't mind, I'll
that was the intent.
I'll take them from the top. So the first one is, can Nexus ZK EVM ensure data privacy while still providing verifiable AI results?
Yes. So just to slightly clarify, it's a ZK VM. The EVM is slightly different thing. So I just wanted to maybe midpoint, but yes, it can. It could. Now, yes, it can with some restrictions. So I would say that because it's a general computing machine, you can't put an AI model and have an output with a proof. The current version of the ZK VM would be honestly too slow for most people. It might take. I don't think it's performant enough in a pragmatic sense today to produce a proof that people. It might take them. It might take them weeks to get the proof. So we're not quite there yet to a point. So if you're using ChatGPT and it takes you a few seconds to get the result, for example, if you just run the ZKVM with machine, yes, it's very much theoretically possible to get the result, but it might take you a long time. So in a pragmatic way, I would say running it on a very fast machine or parallelizing it would be ideal. But yes, it's entirely a performance issue at this point.
Yeah. But that performance will improve, I'm sure. I remember the first time we did a ZKP transaction on Ethereum, and we actually needed 2 full Ethereum blocks to make it work. So I hate. So that would be what in today's money that would be about 60 million gas, and now we're like 10,000 gas. It's incredible the difference that a bit of work makes actually in these fields. So I have a few. Sorry, go on.
Go ahead.
Well, I was going to go on to the next question. So, okay,
Please.
Right. So I thought you gave some of these, but maybe people would like a few more if you have them. It says what are some real world applications of verifiable AI using Nexus ZK EVM?
So yeah, let me just give another one. So the one that I found to be the easiest for people, because people are most familiar with ChatGPT, so I like to give that example, is that um, if you're using ChatGPT, maybe for some reason using you want to know that ChatGPT, you're using ChatGPT 4. Whenever you get a result, you could have a proof that, like, yes, I'm using 4. That didn't swap out to 3.5. Maybe 3.5 is a free version and 4 is a more expensive version. Some models can be quite expensive. Maybe you can get a proof that you're using the model you think you're using. And then the other easy one to understand is there's more and more models generating AI images, and people are saying, "Hey, was that trained on my art, or was that not trained on my art?" Um, there are models that generate images that have Creative Commons art. It'd be really, really nice when you get an image to say, "Hey, this image was generated using the clean data set, not
Yeah.
from stealing other people's art."
Yeah, absolutely. Okay. Oh, yeah, so this is funny you should say that. This is kind of related to that. So could Nexus CK EVM be used to verify AI-generated content and combat deepfakes?
That's an interesting question. So, to some degree, yes. To some degree, no. So, what I mean by that is that the verifiable AI could be used um, to let's say you take an image. So here's a classic example in this space. You take an image, and it's a real image, but maybe you want to publish it on a website or publish it in a magazine. And in order to do that, let's say on a website, you need to resize it a little bit. Maybe you need to make it fit the form factor. Um, you could have a proof that the image was modified, but for legitimate reasons, such as, like, okay, we changed the border, we changed whatever. So this is important because every image you see on the internet nowadays is touched up or modified in some way. There are ways that are more deep fake-ish, where they kind of completely change it, and then there are ways where, no, this is just a valid one. We just kind of resized the image. You could have a proof that when you see an image on the internet, it was modified, but for ways that are what you expect, not for ways that are invalid.
Yeah. Okay, that makes sense. And this is probably a hard question for you to answer. This isn't really a fair question, but I'll ask it anyway. So,
No, I love it.
so you mentioned you've got to get a factor of 1,000,000, and then your verifiable compute's kind of back to where normal compute is. So how far do you think you can get along that road? In other words, do you think there's a kind of hard limit somewhere?
I think it'd be foolish to think there won't be one. I think that, but I think I this the I would say that our intuition and we're bullish on this. We're bullish that we can get pretty far, but it's not quite as binary. So even if it gets 1,000 times faster or 10,000 times faster, there are some things that you are willing to pay that cost for. So maybe there's a very important financial transaction. So there are use cases opening up every time it opens up, every time it gets better. So it's not now or 1,000,000. I think there are certain things that you're willing to wait a little more, pay a little bit more. But I think that we're bullish on the technology and the breakthroughs.
Yeah, and for what it's worth, I would agree with that. The nearer you get, the bigger the volume of applications you open up and use cases, and that's entirely sensible. So, okay, well, we're kind of out of time, unfortunately. So somebody's asked why you chose Rust and not Go or Java, which there isn't time to answer other than Rust is brilliant. Why wouldn't you choose Rust? So I'll just say thank you very much, Diego. That was utterly brilliant. I really enjoyed it, and it's good to see such interesting work going on. And I wish you all the best with it.
Thank you very much. Really appreciate it. Cheers.
Okay, bye for now.